Hi guys, I'm back. I'm going to work through some of the examples of the gas laws problems with you. So these are some of the problems that are on the worksheets to follow. So make sure that you are copying this down as you go and taking good notes because we will have completed several of the problems that you're assigned. So we're going to start with the first problem on everybody's worksheet. Number 1, a gas is enclosed in a 10.2 liter tank at 1,208 millimeters of mercury. If the gas is transferred to a 32.6 liter tank, what will the new pressure be? Now, before I even work through this problem and decide which of the gas laws is appropriate to use, I'm going to list what I know. So I'm going to read through the problem again and write down the values that have been given to me. So a gas is enclosed in a 10.2 liter tank. Okay, the first number that's given to me is 10.2 liters. It's important for you to recognize that liter is a measurement of volume. So volume 1 is going to be 10.2 liters. Okay, and I'm writing this down, and I will show you my work as I go. This is how I want you to set it up. Gas is enclosed in a 10.2 liter tank at 1,208 millimeters of mercury. So millimeters of mercury is a pressure unit. So that's going to be my P1 in my equation because it's the first pressure that I've been given. And that's millimeters of mercury. Okay. If the gas is transferred to a 32.6 liter tank, liter again tells us that that's another volume. So that's V2, 32.6 liters. What will the new pressure be? So I want to find pressure. So this is what I know. I know volume and pressure 1, I know volume 2, and I want to find pressure 2. So because I'm given just volumes and pressures, that tells me that I'm going to be using Boyle's law, and I'm going to be using the relationship P1V1 equals P2V2. Okay, then what I'm going to do is just plug in what I know into the equation and solve for the one that's missing. P2 is missing, so that's what I'm going to solve for. P1 is 1,208, and that's millimeters of mercury. That's going to tell us what our final volume units are going to be. So even if you don't really know what to do with the units at this point, you want to make sure that they are matching. If I was given atmospheres, then my pressure that I was looking for would be measured in atmospheres. If I was given volumes in milliliters, then the final volume would be in milliliters. So watch your units as you do this. So 1,208 millimeters of mercury times 10.2 liters is equal to pressure 2, which is what we're looking for, times 32.6 liters, which is my volume. Then I'm going to solve for P2. So 1,208 times 10.2 divided by 32.6 gives me a pressure rounded to 3 sig figs because that's what I've been given in the problem of 378 millimeters of mercury. Okay, let's work through one of the Charles law problems. So if you could write this down, I already told you this is Charles law, but if you didn't know and you were solving the problem on your own, you would just want to do the same thing. Write out what you know and figure out what you're looking for, and that'll tell you which of the laws you're going to be using. So a sample of oxygen gas occupies a volume of 12.2 liters at 27 degrees Celsius. What volume would this sample occupy at 159 degrees Celsius? Again, I'm just going to go through the problem and list what I know. The first number I'm given is 2.12 liters. So that, because it's liters, means that that's volume 1. At 27 degrees Celsius, that's my first temperature. I know that temperatures need to be converted to Kelvin, but I'm going to list everything as it's given first. What volume will it be? So that tells me I'm solving for V2 at a temperature of 159 degrees Celsius. So the first thing I want to do is convert my temperatures because I know everything has to be in Kelvin. So I'm going to add 273 to my Celsius temperatures. That gives me 300 Kelvin as T1. And let's see, 432 Kelvin as T2. So here's what I know. Volume 1, temperature 2, I'm looking for volume 2. So because of the variables that I've been given, I know I want to use the relationship between volume and temperature. Even if you don't know this is Charles' law, you want to recognize that this is the relationship we're looking at. V1 over T1 equals V2 over T2. And then again, I'm going to just plug in what I know. 2.12 liters over 300 Kelvin is equal to V2, which is what I'm solving for, over 432 Kelvin. Now, it's important to remember your basic algebra skills here, guys. We are going to be solving for this unknown variable right here, okay, volume 2. So we want to isolate volume 2. That means that we have to get it by itself. So in order to get it by itself, we have to multiply by whatever's on the bottom of this fraction. We're going to multiply both sides by 432 Kelvin. Okay, so in solving this problem, I'm going to cancel out the 432 over here. I'm left with volume 2 all by itself. And then over on the other side, I'm multiplying that 432 by the 2.12 liters and then dividing it by the 300 Kelvin. And that'll give me volume 2. So let me just solve this. Why don't you guys solve it with me? 432 times 2.12 divided by 300, and that gives me a volume of 3.05 liters. 3.05 liters. Okay, it's always important to make sure that your numbers make sense. The relationship here is a direct proportion. So if the temperature goes up, that means that the volume should also go up. If the temperature goes down, the volume should go down. Okay, let's work through a couple more problems here. Again, these are all on the worksheet that you are assigned on GoFormative. So do them as we go, and then you'll have quite a few of the answers done already, and you'll have a lot less work to do. All right, next one, we're going to do one of the Gay-Lussac problems for you technical chemistry people. It is number 9. Let's see what it is for my honors people. Which problem are we looking at? The pressure of a sample of chlorine gas. Sorry, guys. It's number 17 for my honors people. So the pressure of a sample of chlorine gas is 1.023 atmospheres at 20 degrees Celsius. What is the temperature if the pressure is decreased to 0.05? 42 atmospheres. Here's a tricky one. We're solving for temperature. And temperature is always on the bottom of our fractions, so that makes it a little bit more challenging to solve for. So watch carefully, watch your algebra, remember everything you learned about isolating variables. So let's list what we know. The pressure, it tells us, this is the pressure, P1 is equal to 1.023 atmospheres. At 20 degrees Celsius, so that's T1. What is the temperature? So it means we're solving for T2 at a pressure of 0.0542 atmospheres. Okay, so here's what I know. This is what I've been given in the problem. I'm solving for pressure 2. No, I'm sorry. I'm solving for temperature 2. And I know all of the other variables. So we're going to start off again by converting your temperature. So we're going to take our first temperature, 20 degrees Celsius, add 273. We have 293 Kelvin as our temperature 1. And now we're going to plug those values into our equation. Remember, the pressure-temperature relationship is P1 over T1 equals P2 over T2. Okay, we're going to solve for T2 in this case. So we're going to take P1, 1.023 atmospheres. We're going to divide it by the temperature, which is 293 Kelvin. We're going to set that equal to pressure 2, 0.0542 atmospheres divided by our unknown temperature 2. Okay, so this is how we would start. Now, because our unknown variable is on the bottom of our fraction, we want to get that on top, because the only way to solve for it is for it to be on the top of the fraction. So first, we're going to multiply both sides by T2. Okay, then T2 cancels out on that side. Then we're going to isolate T2, which means we're going to do the opposite with these variables here. Whatever's on the bottom, we're going to multiply the other side by. Whatever's on the top, we're going to divide the other side by. So we're going to take the temperature, 293, and multiply that by our second pressure, 0.0542 atmospheres times 293 Kelvin. And then to that, we're going to divide by that first pressure, 1.023 atmospheres. Okay, solve with me, guys. 0.0542 times 293 divided by 1.023 is equal to a temperature of 15.5. I'm just guessing at sig figs. I didn't even really look, actually. Kelvin. 15.5 Kelvin. It's really cold.